Hello, ladies and gentlemen. Today we're wrapping up our last little bit of notes for the unit. Our goals for this section is that you can understand how conservation of mass is represented in a reaction, and that you can wrap everything together in a flow chart that shows the relationship between physical and chemical changes. Conservation of mass is something we observe for all changes that occur. Any time that you have a physical or chemical change, you are going to have to finish with the same mass at the end as what you started with. So whatever your products are will be equal to the mass of your reactants. Think for a moment about breaking apart water. Let's say I had 15 grams of water that were completely broken apart, and I see that I end up having 5 grams of hydrogen. If I know that the only other thing that's being produced is oxygen, then by default I have to have 10 grams of oxygen left over because 5 plus 10 equals 15. Now, what I will tell you is that that example is not accurate because it's not tied to the actual masses of the substances in terms of their atomic masses, so the proportions are off, but the idea is correct. If I start with 15 grams of matter, in total I need to finish with 15 grams of matter. This is true for any physical or chemical change. So this is also just like our separation of a mixture lab. If our percentages were not exact, there was something in the procedure or some loss or gain of material that we could account for. Now, we are wrapping up an entire unit about properties and characteristics of matter. So over the course of this unit, we have classified many different things. So in terms of types of matter, we said you can have pure substances, which has specific sets of properties, both chemical and physical, or you can have mixtures. The biggest difference between them is the distribution of the particles and what types of things make them up. Every component in a substance is going to be the same as every other component, where in a mixture, they may not always have the same composition. So in a substance, that would be homogeneous by description because every part is consistent and uniform. If I would want to break apart a compound, which we said is made of 2 or more types of elements or atoms, I would have to separate that chemically because they are created chemically. If I look at mixtures, we said those can be pulled apart physically because what substances are in there maintain their characteristics. And we then classify them by their distribution of the particles. If everything is evenly distributed or uniform, we said that's a homogeneous mixture. If it is not uniformly distributed, often when you have maybe a solid with a liquid component, those would be heterogeneous. Remember, that's like the chicken soup. Maybe in 1 spoonful you get a noodle and 2 pieces of chicken. In another spoonful you might get more broth and only 1 piece of carrot. What they are determines how you can separate them. So remember, because the mixtures are physically put together, we can separate them physically and put them back into their individual pure substances. Last little piece. Remember, atoms are the most basic particles of matter. A compound is going to be some chemical combination of at least 2 or more types of atoms. But if I'm talking about an element or a compound sample, both of them are made of many, many, many atoms in that sample.